I'm going to go to, we have correlate and bivariate correlation, and that's what we're doing, right? Of course, this is bivariate correlation. We have two variables. Bivariate correlation, I'm going to put both of them in there again. Doesn't ask me which one's the dependent, which one's the independent variable, because it doesn't care. It's just looking for the association. And we're going to calculate Pearson's chi-square. I'll click OK, and I'll do it again so we can raise it up and see it. Okay, and here's our calculation of correlation. Okay, our Pearson's correlation is 0.821. That's the number I should have got when I did the cell calculation. I'll go over it and see if I can't figure out what I did wrong later on. Okay, so what's our null hypothesis? That there's no association between age and blood sugar, right? And what's another way of saying that? R is equal to 0. Our alternative hypothesis is that there is an association. Does it appear that there's an association? And is it a good association? Yeah, 0.821. R is 0.821. Can we reject our null hypothesis? Not yet, right? That could be due to chance. We have to know what the probability of getting that result if there's no association. What is that p-value? Or what SPSS called significance? It's 0.004. So now we can reject the null hypothesis. We have the magnitude of the association, and we also have evidence that we can reject that the null hypothesis and say that there is an association. Okay, so now we're going to take it to the next step. We're going to say analyze, and this time we're going to go to regression, and I'm going to go to linear regression. You notice that there's many other ordinal regression. We were talking about that before, logistic regression, so on and so forth. We're right now just interested in linear regression. Okay, so in this case, it's asking me which is the dependent variable, which is the predictor variable, which is the outcome variable, or the dependent variable. The independent variable is age, right? That's the predictor variable. Independent variables are predictive. And the outcome variable, or the dependent variable, is going to be blood sugar in our case. Okay, so let's see if there's anything else I need here. I'm sorry, what's that? Was there a question?
Regression and then linear. Sorry, I just missed
you want me to see? I'm gonna do it twice anyway, because I have to.
Sorry.
Yeah, because I want to make sure we can see the plots. Analyze, regression, linear. Okay, and move the dependent variable and the independent variable. The x is the x is the independent variable, and the y is the dependent variable. Okay, and click OK. Okay, and here's my calculation. Okay, let's see, regression. Okay, well, let's take a look at this. R squared, what's R equal to? 0.821, same calculation that we did before for correlation. What's R squared is equal to 0.674. It's telling us that 67% of the variability in blood sugar can be explained by age, person's age. That's a pretty good correlation, right? I mean, the idea that, if it were real, that would be very interesting, wouldn't it? That, like, of all the different things that could impact blood sugar, that one is a major factor, right? So that's why that's important to us. Okay, so now let's take a look at this, and this is our calculation. Remember, Professor Waldron might have mentioned that this can be basically this is a kind of analysis of variance that you're doing here, because you're looking at we just did a whole bunch of sum of squares and calculating variabilities and so on and so forth. It's a form of analysis of variance, and in fact, that 0.0004 that we got for our correlation, that p-value is from this analysis. Okay, it didn't show it to us before. Okay, then finally, the last box we have is a box which tells us, did I do this twice?
Coefficient.
Yeah, coefficients. Let me do it again. I thought I had done it twice. I did the other one twice. Right, okay, good. Let's say okay. Yeah, we go. Now I got it twice. I want to be able to get this box. There we go, there's the coefficients. Numbers look familiar? If I look under the coefficients here, right, this one that's called constant is our y-intercept. And this one that's called age is our slope. So the formula for our dependent variable, which is blood sugar, is equal to 1.762 times age plus 17.47. Or another way of saying it is y is equal to 1.762x plus 17.476. Why is that valuable? Now you have something that you can use to predict one from the other. Wouldn't it be nice if we had some physical measurement like BMI? Let's say we did this for BMI. Wouldn't it be nice if BMI were a super good predictor of heart disease? Right? Well, then we wouldn't have to put people on treadmills. We wouldn't have to, do angiograms. We wouldn't have to do all this other stuff. We could just measure their BMI. But as it happens, it's not a good predictor. It is maybe it's a predictor, but it's not a really good predictor. In other words, there are so many other factors that are involved that maybe only a few percent of the variability in the rate of heart disease is due to BMI, right? But the greater this relationship, the more that we can say it's due to this. So this coefficients table is what you're going to use to get your formula.
Is there a rule of thumb on how good a predictor can be?
No, well, it's going to be different for everyone, right? In other words, and then you'll have to make a judgment as to whether it's going to be clinically useful for you. The p-value tells you whether it's statistically significant, whether it's real, right? And you can reject a null hypothesis that there's no association, right? But how clinically significant it's just a judgment you have to make, whether it's going to be useful to you or not. Okay, so let's take a look at another one. I think I have some more of these. Minimize this for a second. Okay, let's see what else I got here. Arsenic and well water. That's X. Let's see if I got that. See if I got that as a. There it is. What was our use? Uh-oh. It clicked the wrong one. We only have the Excel file? Yeah, I only have the Excel. That's okay. How are we going to deal with that? I'm going to open that SPSS. Okay. I'm going to say File, Open, Data. And I can import many different forms of data into SPSS. Right now, the only thing it shows me are the files that are SPSS data files, .sav files. However, there are other files in that folder that we saw when we had it open on the desktop. So I'm going to say, well, let's see, instead of just looking for SPSS files, show me all files. If I go down here, it'll show me all files. So now I can see that I have arsenic and well water as an Excel file. So I'm going to say to open that. Okay, Windows is going to come and tell me that it found data in row A1 through H329, and it's asking me, do you want to read the variable names from the first row of data? Honestly, I don't remember. Anybody remember? Was there names on? I think there were there? I don't remember.
I got it open. Yeah.
There are. Okay, so I'm gonna leave that checked off. No.
No.
No, it's just blank. Okay,
No,
so
I didn't open it.
Oh, okay. I'll give it a try too on mine.
Yeah, it does. It has about
variable name on the top.
Variable.
So the top row has the variable name, right? So I'm going to leave that checked off. So it will use that as the variable name. If I got that wrong, if I unclick that, it would try and read that as data, right? That top line. If it was the other way around, that there was no variable name, it was just data right from row one. If I check that off, then it would try and use that first value as the variable name, which if it's a number won't work anyway. And then it would, if it did work, you would lose that line of data, right? Because it wouldn't realize that it's data. So I'm going to click OK, and it'll import it. Okay. Now the only thing that you wind up losing here is that if I go to the variable view, it's not coded. It may not be coded correctly. Okay. So this is well ID, subdistrict, town, right? Town, subdistrict. They're nominal data. It got them right. Latitude, longitude, depth, year. It looked at year as nominal data. It could be nominal data. Arsenic as scale data. Okay, it looks like it got it pretty much right. For the nominal data, it didn't. It doesn't know what the categories mean. It doesn't know if it's a town name or it might be like certain regions represented by number one, number two. You'd have to fill that data that definition in there yourself later on. Okay, so I'm going to go back to the data view, and really all I'm interested in now is I'm interested in whether or not there's an association with the depth of the well and with arsenic. Why would there be an association between arsenic and water and the depth of the well? Yeah, it's minerals, naturally occurring mineral in the ground. Deeper the well is, the more minerals that water has been seeping through. So in general, I mean, you say deep wells probably have more minerals dissolved in it than say shallow wells or say certainly surface waters than lakes and lakes, streams, reservoirs, rivers. They have very little minerals in them. They're very soft waters. Waters that are deep in the ground tend to be very hard water. They've had a lot of time to percolate through the ground and dissolve a lot of minerals. So that would kind of make sense. The UN in the 60s, I think it is, there was an enormous problem with waterborne diseases in India. And the UN set up a program where they provided equipment and expertise for going into towns in rural areas of India and helping them set up dig wells, dig wells, and use groundwaters instead of surface waters because the groundwaters are less likely to be contaminated with pathogens than but one of the problems there is that many of the regions where they did this had high levels of arsenic in the ground, and they wound up protecting people from the pathogens, but then there was an enormous problem with arsenic poisoning in these same communities. I'll bet you if you Google UN, United Nations, and arsenic and wells, you probably find some articles about this. So yeah, this is something that might be interesting to us if we can predict whether or not a well, if we could, let's say the arsenic level, we don't want an arsenic level above a certain amount, right? But we want to dig it deep enough so that it's less likely to have pathogens that are seeped in there from the surface. So we want to get the best depth, but without getting too high an arsenic level. It might be important to us to be able to predict what the arsenic level might be at a given depth of well. Okay, so we can say let's only dig to that depth, or we're willing to exchange. We have such a big problem here, we're willing to go a little bit deeper. Right, so let's take a look at these two numerical variables. So I'm going to go to analyze. I'm going to go to correlate. Actually, first I'm going to what's a good thing to do first? Let's do a scatter plot, see if there's an association. Okay, and let's see. We're going to put depth into our x-axis. I think that's probably going to be our predictor variable, and our dependent variable is going to be arsenic. See if there's an association between depth and arsenic. Kind of hard to see, right? Why is it so hard to see? Because so many of them have no arsenic in them, zero, right? But it looks like there could be a bit of an association. Oops.
Yeah.
Yeah.
So like.
Yeah, it looks. I would have thought it would have been the other way around, but it looks like the greater the depth, less likely. Maybe because in this region, the areas where those minerals are that it might leach are a shallower depth. Okay, so let's do it to see what kind of association this is. Analyze, correlate, bivariate. Okay, and I'm going to put in arsenic, depth, the well, and arsenic. And I'm going to say okay. Okay, and I'll do it again so we can scroll up. Okay, so what is our correlation? It's negative 0.25. So what does that tell you? There's a negative association. Deeper the well is, the less arsenic that you find in it. Okay, so surprised me, but I mean that might be exactly what you might be interested in. It might be better to dig a deeper well in this region than a shallower well, based on the samples, random sample of test wells that you might have dug. And maybe you don't have the resources to keep testing them. So you want that information. Okay, so now let's try and use this to predict what the arsenic level might be at different depths, and also to see how good a predictor it is. Let's see, regression, linear. Okay, my depth is going to be my independent variable. My arsenic is going to be my dependent variable. I'll click OK. Okay, I'll do it again. Okay, so we can see this. Okay, see what we have. Okay, r squared is equal to 0.25. R is equal to 0.25. That makes r squared 0.6. Only 6% of the amount of arsenic in the water can be predicted by the depth of the well. Right? The variability, only 6% of the variability in arsenic levels. Not a very practical tool, right? Because there's other factors apparently that are causing this to be an issue. Can we say with some level of certainty that there is an association? Well, yeah, the significance that we found is 0.000. There's an association between depth and arsenic. It's just not as good a predictor as we would want to be. There's too many other factors that have some influence. This definitely has a influence. And what is the line that best fit line? What's the formula for our best fit line? Well, the formula for our best fit line is, I thought I did it twice. We got to go back up further. There we go. It's going to be the amount of arsenic present is going to be equal to the depth of the well times, let's say meters, I guess, depth of the well times minus 0.669 plus 140. Okay, that's going to be the line. It's going to be predicted. So if I want to go somewhere and I'm going to dig a 200-foot well, I can plug those numbers in and hope that it helps me predict what the arsenic levels are.
Can you repeat what the equation is?
I'm sorry, say again.
Can you repeat what the equation would be?
The equation is going to be, so if we go in here to, when we see our coefficients here, the constant is going to be our y-intercept. And it actually puts the variable name here, and that's going to be our slope, right? So if we look at it as y plus y and x, the formula is going to be y is equal to negative 0.669 times x plus 140, right? If I substitute the actual variable names, it's going to be the arsenic level is equal to negative 0.669 times the number of meters deep that the well is, plus 140. Okay, so that's going to be my best fit line for this output. Okay, let me see how we're doing here. On time, we're just about at 7:45. We've got a couple of minutes left. Any questions that you guys have right now on this stuff? In other words, if you were to go to the community health data, right? It has, I think, 7 or 8 numerical variables out of 9. They're the minority by far, right? I think there's like 200 variables or something like that. But there are some. There might be more than that. Maybe I'm going to revise that. Say there's 10 to 20 numerical variables. There's certainly age. There's certainly weight, BMI. I think they have BMI. I think they calculate the BMI for your height, ounces of number of cigarettes or something like that, ounces of soda that you drank per day, number of pieces of fruit. I maybe not. That might be categorical. I'm not sure. But there's certainly numerical variables there, right? So you can actually we have this file, the Community Health Survey, in SPSS in an SPSS format. If it isn't on Blackboard, I'll make sure it is tonight. As a matter of fact, I think if it isn't on Blackboard, where the final project tab is. It was in the material for last week's lab. I'm pretty sure the code book and the converted data set for SPSS were in there. You might have to fill in do some formatting of the variables, so it makes a little bit more sense. But the actual numbers are all there. So you might want to go through that and see if there's some numerical variables that you might want to play with, that you might want to use in your project, right? So if you go back to the slides now, you'll start to see where this idea of correlation and regression ties into to these slides that he was working on, and what those values meant, and how you use, again, like analysis of variance. How do you use the variability of these two values to see if there's an association between them? Just as we use the variability to see if we could say that the two means of multiple groups are different from one another. Right? It's kind of interesting to be able to use variability as a tool like that. I want to show you one more thing, and that is, now that we've created that formula, right? Now that we've created that formula, I'm going to go up here to Analyze, Descriptive Statistics, excuse me, not Descriptive Statistics, Regression, Linear, okay? Now, one of the tabs that we have over here on the right side is Save. I'm going to click on Save. Okay, there's some surprises in there. Okay, so now what it can do is, I'm going to click off this, see there's a box here, predicted values. I'm going to check that off, okay? I'm also going to check off residuals, unstandardized residuals. I'll tell you what that means in a second. But basically, I'm just going to ask it to give me the predicted values and the residuals. What are the predicted values? Well, for a well that's 50 feet deep, it's going to take that formula, apply it, and tell me what the depth is, what the level of arsenic is. Okay, so let's do that. Continue, and okay. Okay, so it does everything it did before. Okay, and let's see. Okay, I don't see any differences there, right? See residual statistics. It gave me an extra box there. It doesn't really tell me too much. However, look what happens when I go back to the data view. Where is it? Let me get down here to it. Let's see, view. Oh, this is the output. Okay, good. I'm gonna get back to my data view. No, that's the H. It's the other one. I think it's the other one. That's it, right? Okay, now look what happened here. All of a sudden, I have a couple of extra rows here now, right? This is my predicted value for the arsenic level, right? So the depth was 60. It plugged the 60 into the formula that was created and came up with an arsenic level of 100. The actual level in that particular well was 331. What's the residual? That's the difference. That's the difference between the predicted value and the value that we actually, and the value that was actually there. So these are all the different residuals, all the different differences. And that's part of what we calculated when we did the variability, is to examine all of those. One of the things that we're interested in is whether or not these residual values are random. In other words, that they're not very small differences at one end, low at one end where we have relatively shallow wells, and very scattered, bigger residuals, bigger errors where the well was deep. And in fact, remember what that data looked like with that weird cluster of very low value? I think that's going to happen here. I think that's one of the things that makes this data less reliable, less useful, and gave us that R square of only 0.06. I think that ties into this. So those are the reasons you can actually calculate the residuals. If you wanted to do it manually, all you had to do was actually plug the numbers into the values, but SPSS does it for you automatically. Okay, so this is another tool we have. We've got descriptive statistics, so you can describe what your population is, what their ages are, what their average age is, what the proportions of male and female are, what the proportions of ethnic groups are, what the so on and so forth. You can predict you can describe your population. You have t-score, the t-test, right? Your hypothesis set t-test. If you want to compare two groups in terms of a numerical variable, do men smoke more cigarettes than women do in New York City? You have your analysis of variance. If you want to compare a numerical variable for multiple groups, multiple groups within a variable. Let's say the ounces of sugar, average ounces of sugar that are sugary drinks that are drunk by different ethnic groups. And we have chi-square for when you want to see if there's an association between categorical variables. Let's say gender and frequency, gender and say depression or something like that. Have you ever been? I don't exactly kind of funky questions they ask about depression. Have you ever been blue for more than a month or something like that? And that'd be 1 and a 2, yes or no. And gender might be 1 and 2. You can compare those so you can see if there's an association. And you would use chi-square, or you would use odds ratio or relative risk for that. Or numerical variables like this. Associate one numerical variable, see if there's an association with another numerical variable. You can use correlation and regression. Okay, so the real key here now is that as you start to think about what you're going to do for your project, find some interesting data. We got 200 variables in the community health survey. Or you might find your data somewhere else. Think about, well, now, one part of this is I have to describe this population, given my descriptive statistics, what my averages are for the values that I'm interested in. Okay, and say to yourself, okay, this is how I'm going to present this. Oh, maybe a good graph would be useful here, a bar chart, or maybe a histogram would be useful here to describe how this population is distributed, in addition to a table with the numbers. Now I'm going to put together, I'm going to introduce the variables that I'm examining. Okay, let's see, I'm going to examine these two variables. Well, let me give them the mean, let me give them the numbers, let me give them so on and so forth. And now maybe a column chart, a bar chart, the males versus females, insured, not insured. Maybe that helps describe stuff a little bit. Okay, and now I'm going to decide what statistical test I'm going to do. So now I'm going to put in my poster. I'm going to put in my what test I'm going to do. I want to do a odds ratio, and I want to do chi-square, right? Because it's categorical data, right? So I describe what my value, do the chi-square values, put my boxes in there, state my null and alternative hypothesis. Then I put my observations and my conclusions, and I say, well, this is what it looks like is happening here, and so on and so forth. So you have a really nice organized poster. Did we post any sample posters from previous semesters? I'll talk to Levi about this.
That was perfect.
That would be really good.
I'll see if I got some pictures also. The deal is that we're going to take, those like 3 foot by 4 foot pieces of foam core board, right? Like poster board, right? And you're going to print out your poster on 8.5 by 11 sheets of paper. And we're going to give you push pins, and you're going to pin your posters up to that. Have you guys seen what posters look like? Yeah, let's look at the podium. For those of you that haven't, here's what a poster session looks like. Oh, I got to take this back, don't I? Okay, hang on a second here. I'm gonna bail you guys out here in just 1 second. Okay. Let me take this back here. Okay, I think I got to do this. Okay, make presenter. I should come back to me. Okay, good. Just this one last thing. Poster session. Okay, APHA, American Public Health Association. Let's see if I get lucky and find one of theirs.
I think
Here you go. Here's a poster that someone did, right? Yours is not going to look like this, right? Yours is going to be like, kind of like really pretty primitive, right? But you get the idea. You get what these people are doing. They are presenting. Not everybody gets to stand at a lectern and lecture to 200 people on their research, right? That they just published in Science Magazine. There are hundreds of these that might be presented at a big conference like the American Public Health Association. And what they are posters that are introducing to other people that may be interested what these people are doing research on, what they found, what they're working on, but maybe they haven't gotten all the data they need yet. They're not ready to publish. But you can walk through rows and rows of these things. And you can all of a sudden say, aha, look, this guy's doing research on Legionnaire's disease. That's my interest. I'm going to go over here and look at this poster, see what he's doing, talk to him. And so they'll be standing there. They'll be standing there with their project, and just like that, just like she is there, and they will be in a situation where they can explain to you what they're doing and present their data and so on and so forth. Right. So, I mean, that's kind of what we're doing. We want you to get a feel for what it is like to do actual research and then analyze it using statistics. It would have been a hell of a lot easier for us to give a final, trust me. Because when we do this, we're going to have to give everybody 5 minutes or so to do their presentation, and there's 30 people in here, and everybody's going to go long, and it's going to be, and we have to try and make a judgment and grade. It really is miserable trying to grade this stuff. But we think this is going to be a more valuable tool for you in the future. That like you'll be forced to like kind of take data, try and figure out how you're going to present it in an organized fashion, and what kind of tests you're going to do, and so on and so forth. Okay, and I think you'll have a good time doing it. Certainly more interesting than staying up all night and studying for a test anyway. Okay, and every once in a while we have poster sessions here for different research that students here are doing. We had one last. Did we have one in the spring? You got to be here on the right night, unfortunately, unless you're keeping your eye open. Yeah. Here, there's a poster session here. You can see rows of these things just hanging up there and stuff like that. Okay, so good night, guys. Good night, guys, online, and get started on your projects. And at least you got the heat. You don't have to deal with getting ready for a final or something like that. But try and channel that energy you would have put into studying for a final into doing something interesting on a project. The first thing is you got to deal with is picking what data source you want to use, what you want to show, what you're interested in, and there's enough data in that community health survey and the other data sets that I think you'll find something in there. If you go through all of those 200 variables, you'll find something in there that you're interested in, whether you're a nutrition person or infectious disease person or a sports medicine person. You'll find something in there that I think will interest you.
So,
Okay.
So if we want to present an association about causation.
Well, but you want to find something in there that you're a public health person. So if you're into sports medicine, you might want to see, well, is there an association between diet and whether a person is active? Is there an association between activity and whether a person reports they have diabetes? It's gonna have to be something you're interested in. Yeah, I can't tell you what to do because you'll do something. I just told you Legionnaire's disease. I'm interested in Legionnaire's disease, right? You may have no interest in Legionnaire's disease. So I can't be the guy to pick out those variables for you. You got to pick out something you're interested in. What they always say, if you pursue stuff you're interested in, you'll always do better at something, right? Because you'll be more motivated and wind up doing a better job at it than if you're forced to go a certain direction. Yeah, you have to give it by what is it, the 21st?
Like when we present our poster.
Oh, you got the choice. You could either do the 21st or you could do it next week. I think we timed 5 minutes or 6 minutes or something like that. That's a lot of time. You'd be surprised. That's a lot of time, especially the poster, the poster's telling the story. You're really introducing the poster and summarizing what's on the poster, But I don't think we really, it wasn't like we had a hook, like in the old vaudeville thing. There were no hooks involved. But yeah, we time it. We do time it and encourage you to not go on forever. Okay? Okay, and there's a thing on Blackboard that if you are making some progress with this, you can sign up to do it the week before, the 14th instead of the 21st, right? Which is next week. Where'd the time go? Right?
So for descriptive statistics, we have to describe the population.
Well, first of all, number one, if your variables are blood pressure and ethnicity, you might want to tell us what proportion of the population that you're examining was white, African American, Pacific Islander. What percentage, what that population looked like, and blood pressure. What is blood pressure? What was the variability in blood pressure? In other words, what was the mean blood pressure for the whole population? What was the variability in blood pressure? And then, if you're really trying to show that different ethnicities have different average blood pressures, then you would do your test, your statistical test, and separate out the average blood pressure for Hispanics and for whites and for African Americans and so on and so forth. Right? So, yeah, statistics, descriptive statistics are going to do both. You're going to be descriptive statistics will describe the general population you're working with, New York City people, males and females, and the descriptive statistics may also give us an idea of what the average blood pressure and what the distribution of the different ethnic groups is in New York City. And then you can go on and do your other stuff. So descriptive statistics covers a lot of ground. Not just it covers generally what the population looks like, especially the parts of the population which may be relevant. In other words, if you're looking at something that you're looking at weights or something like that, then it might be important to describe what the proportion of women and men are, because then they have two groups that have different weight, average weights and so on and so forth. But then if you're looking at some other variable within those groups, then you want to maybe give some descriptive statistics on that as well. Remember, descriptive statistics: mean, standard deviation, range, interquartile range, that kind of stuff. Box plots, histograms.
And how many variables do you recommend that we do?
As few as possible.
Okay.
Don't get nuts.
Okay.
In other words, you're not going to get extra points for doing 70 variables.
Okay. No. Right. What's a good number? You would say like 3, 2, 3, no more than 3. Like...
Well, it depends on what you want to show. I mean, it's entirely possible that you could make, and you remember, you're also going to have some background. Maybe you'll cite some previous studies or something like that have been done on this, right? So you may, you may just be doing a t-test and comparing, two populations for some numerical variable. Right? It might be that simple, but then you'll have some background. You'll have the description of your population. You'll have the results of your t-test. You'll have your observations, your discussion, like what you think you've shown, and so on and so forth. Give it a try.
Yeah, because I did my descriptive statistics, and I felt like I didn't have enough I didn't describe enough of the population. I only found like the frequencies, but I wasn't sure if I needed to do more than that.
What are you trying to show? What's your?
I'm comparing. I'm trying to find an association between the flu shot utilization and gender, and also the nativity of the population, if they were like U.S. born or foreign born. So
okay.
It's all categorical.
Okay, so a categorical variable. So for starters, you might want to show what proportion of the population was born here and how much was foreign born. So there's a bar chart right there, right? And there's a little table, percentages and so on and so forth. You might want to show what percentage of the population in New York got flu shots overall, and so on and so forth. You might want to show the gender. You might want to so on and so forth, the age distribution.
Yeah, that's what I was
Right,
thinking.
right. And, just to describe, you might want to describe the population in New York, but then you might want to get specific and look at the descriptive statistics for the variables you're working with.
Yeah.
Right? In your case, it's three:
Uh-huh.
gender and nativity and flu shot. So you have three variables, right? So you might want to show that, right? You might want to look up some literature, see if there's something in the literature about previous studies that suggested, maybe, why women might be more likely to take a flu shot than men and so on and so forth. And then you're examining it for this population, right? And then you might want to do a test. In your case, it might be chi-square, it might be odds ratio, and so on and so forth.
Okay.
What are the analysis just yet, which we're just looking at like the demographics of our population?
Well, yeah, remember, you got two things you could do descriptive statistics on. One is the population in general, right? Okay, so, but you have to make a decision. In other words, if you think that the variables that you're going to be examined, that knowing the distribution of age in that population is important, you would want to say up front, well, I'm examining 2,000 people in New York City from the community health survey, and 40% of them were female and 60% of them were male. If, maybe you might want to give a distribution, the average age, the distribution age, or something like that, if that were relevant to what you were doing. Right? In other words, maybe gender is more relevant than ages. So you might want to upfront describe the population. But then you also want to do descriptive statistics for your specific variables. If it happens to be gender, you want to give us some descriptive statistics there. If it happens to be insurance status, you might want to give us a table and maybe a bar chart or something like that for that if you want. And then go ahead and try and demonstrate, tell us what you're going to demonstrate. Give us your hypothesis. Okay?
Okay. I don't know how would you go find what the description of your population is?
It's going to be, you're going to have like 200 variables, right? So, and if you look at those variables, each column represents a different variable. Age, gender. Let me see if I got one available here. Are you guys online? Could you post this video? Yeah, I'll try and get it posted right away if I can. Okay, and okay, you guys online. Okay, so you guys online, you don't have to hang around now if you don't want to. We're kind of like going back and forth with some questions. I'm going to open up quickly. I'm going to open up, if I can find it, the community health survey. Community health survey. Code book. Here's a code book. Okay, let's see what we got here. Okay, so the first variable we come across, general health status. People rated what they thought their health was. 1, very good, 2, very excellent, 2, very good, and so on and so forth. Then you got insurance, various insurance variables. Then you got, let's see, do you have more than one person? Let's see, I've been told that you have hypertension, high blood pressure, right? So you got blood pressure variables, diabetes. I've been told you have diabetes. You have that variable. And these, for every person in this, you have in that column, you have either a 1 or a 2. These are basically non-answers. But you have either a 1 or 2. Yes, I've been told I have asthma. 2, I haven't been told that I have asthma. Right? So you could tell us, 1,108 people out of 9,000 in this survey reported that they had asthma. In other words, it looks like from this survey, 18% of the population in New York City has asthma. Right? And then you might want to look at, say, let's see if people who have insurance are more likely to have been diagnosed with asthma than people who don't have insurance. Right? So that was a variable up here. But you can go through, now hang on a second. Mood, look at all these variables we got here. We got variables on mood. We have a lot of variables on mood. Depression, lots of them. Now here, average number of sodas per day. Ounces of sugar sweetened soda per day. Let's see. Uh, Size. Exercise. How much have you bicycle? Have you walked? How much do you walk? How much have you bicycle? Walk up or down stairs. Number of cigarettes. That's a numerical variable. Right? Number of cigarettes that you smoke per day. Um, um, Smoking. Have you tried to quit? Uh, Dentist. You go to the dentist. Age groups. What age group are you in? What's your age? What age group are you in? A race, ethnicity, country of birth. Are you urban? Were you born in an urban region or a rural region? Education level. Poverty. Are you in a poverty group? Annual income, right? As a percentage of the poverty level. I don't think they ask them the actual number. Uh, how much do you weigh? What's your BMI? I don't know how far am I through here? I'm only halfway through, right? Right, I mean, you can go through this here. Flu. These are the flu shots. During the last 12 months, have you had a flu shot? Yes or no? Right. There's a flu variable. HIV status. Right. Okay. If you have HIV, is a person with HIV more likely or less likely to have gotten a flu shot? That's a hard question to answer. Right? Because if you have HIV, I'm not sure is it a dead vaccine or a live, or maybe different, right? The nasal one. I don't know if they're really dead vaccine that they use nowadays, right? Or maybe it's just fragments of the vaccine.
Questions on like the same people have answered all the
Yeah.
questions.
Yes, it's the same. In other words, a phone survey.
Yeah.
They think about this. They got 10,000 people, and they sat on the phone with every one of them and asked them everyone. I mean, these people. First of all, number one, I've been done after the third question. I got a life here. I have to go. You know.
They have missing variables. I mean, obviously, because
Yeah.
yeah, because it's just like people don't want to sit
Yeah. Well, exactly. Well, apparently there's 10,000 people that had time to do this. So
One time you said they're gonna send me money, and they never sent me.
what's that?
One time you took a survey, said I'm going to get something out of it, like money, and you never sent me. Yeah.
Well, that's not very nice. How many of the unaltered cats? Do you have cats? And you know, cats are important. I think I just saw a article that was reproduced in the Times, that was summarized in the Times, about increased rates of depression in people with cats, and they think it because it's some infectious thing or something like that. Huh? Yeah. Cat explains cat ladies, right?
Maybe something the other way around.
Yeah. But do you have all the cat? What was that? Something.
I don't know if that's the causal.
Right. There you go. Might be some other thing. Yeah. You never know, right? But they do suspect that pets, there may be more parasitic infections or bacterial infections or viruses that than they previously thought that were associated with humans and their pets. All you have to do is you take a look at half the people who have dogs are kissing the dog half the day. So yeah. So yeah, they might have good effects and so on and so forth. Yeah, so you have like so many different variables and so many different kinds of information, categorical variables, numerical variables, ordinal variables. We didn't really spend much time with ordinal variables. We certainly have a lot of tools that we can use to work with this stuff. Okay, so pick the real key here is go in here and pick something that you're interested in. And then say to myself, gee, I'm really kind of curious about whether there's some association with cat ownership and disease, mood, good or bad, or whatever. Go in there and pick out something that looks interesting to you. Because I guarantee you, if you just go in there and pick out variables at random, and you ain't interested in them, it's going to make it 10 times harder to do this.
What about Ebola disaster?
I'm sorry?
Ebola disaster?
Oh, the Ebola data set is very difficult. It's kind of difficult to work with. Have you looked at it? Because it's countries and cumulative cases and so on and so forth.